there's a couple other review seminars hosted by other people, so thank you for coming to this one. And we're just going to go over a mock midterm and answer the questions. Okay. Can you guys all see the screen? Oh, shoot. Hopefully, I can't see the chat, so I'm just gonna go on that. Okay, so for question number one, it's looking at it. We're looking at a transformation matrix, and then it gives us the transformations and asks us to make the matrix. Since both the bases it is being transformed into are the standard bases, we don't have to worry about that. And so to take the transformation matrix, we just take the transformation for each of the standard bases vectors and put it into a vector in this form. So to get t1 of 0, we get it is equal to 1, 0, 2, 0, as it is given in the question. To get t 0, 1, 0, we take t 1, 1, and we subtract t 1, 0, 0, which is -1, 3, -2, 4. Similarly, for t0, 0, 1, we take t1, 1, 1, and subtract t1, 1, 0, and we get 1, -1, 3, 0. So our transformation matrix T from alpha to beta is equal to 1, 0, 2, 0, -1, 3, -2, 4, 1, -1, 3, 0. Okay, for part B it is asking us for a basis of the image of T. Since we know it's a 4 times 3 matrix, we know that there's at most 3 vectors in the matrix, and then we just have to check that all 3 of these vectors are linearly independent. And one way to do that is to take the row-reduced echelon form of the matrix. And so we can put that in. And then to do that, we can do R3 minus 2R1 and get 1/4 of R4. And this will give us 1, -1, 1, 0, 3, -1, 0, 0, 1, 0, 1, 0. And then we can get rid of the third digit in the second row. And we can take R1 plus R4 and R2 minus 3R4 plus R3. And this leaves us with 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0. And then we just swap row 2 and row 4. And we get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. And notice that we have 3 pivots and only 1 row of zeros, so that means all 3 vectors are linearly independent, so the basis of image of T is just 1, 0, 2, 0, negative, oh shoot, 1, 0, 2, 0, -1, 3, -2, 4, and 1, -1, 3, 0. And then, so that's it for part B. For part C, to find the kernel of T, we know that the image of T is the full rank of the thing. Therefore, the kernel T is what's left of it, which there's nothing left. So therefore, the kernel of T is just the empty set. For the other questions, there are a couple questions that we made for the practice final. I think it's question 3 and a couple others. If you guys want to stay for that as well. Okay. I'm just going to get started on question 2 then. Question 2 is also pretty similar. It is a transformation question, but this time the basis is 1x squared instead. So to take the transformation of that, we take the transformation of each of the items in the basis. So t of x, and t of 1, t of x, and t of x squared. So t of 1 in this function, we plug it into the function. Since 1 is like a constant, there's no x in it. If you plug it into the function, it's just going to be the same thing. So we get 1 plus 1 times x plus x squared, which is equal to 1 plus x squared. And then written in the in terms of the basis, we get 1 1, 1, 1. Similarly, for t of x, p of when p is equal to x, you plug it into this function. X is equal p of -1 would be -1. P of 0 would be 0 times x. P of 1 is 1 times x squared. And then we get -1 plus x squared, which gives us, in terms of the basis in alpha, is -1, 0, 1. For x squared, p of -1 is 1 plus 0 times x plus 1 times x squared. And we get 1 plus x squared. And in terms of the basis alpha, we get 1, 0, 1. So for this, our transformation matrix would then be -1, 1, 1, -1, 0, 1, 1, 0, 1. Part B is asking us to compute the eigenvalues of A. Recall that eigenvalues fulfill determinant of A minus lambda I equals 0. So we can take the determinant of A minus lambda I, which would be 1 minus alpha, -1, 1, 1, negative lambda, 0, 1, 1, 1 minus lambda. And then we're going to use the middle row to find the determinant because there's a 0 in one of them, and we can skip a term when we're doing it. So we get from this -1 times determinant of -1, 1, 1, and 1 minus lambda, plus, oh wait, no, not plus, minus lambda of determinant of 1 minus lambda, 1, 1, 1 minus lambda. From there, we get -1 plus lambda minus 1 minus lambda 1 minus 2 lambda plus lambda squared minus 1. And that leaves us with 2 plus 2 lambda squared minus lambda minus lambda cubed. And then usually you would do polynomial division and test the roots for this, but this one is a little bit easier for us. We can do group factoring to find the roots for this polynomial equation. So we get 2 plus lambda squared minus lambda times 1 plus lambda squared. And this gives us 2 minus lambda, 1 plus lambda squared. And from this, we get eigenvalues to be equal to 2. And this is the real one, and I and negative I. I'm not sure if you guys take the imaginary ones, but I'm looking at the question and it's only worth 4 marks for part C, where you calculate the eigenvectors, and I think it's a lot of work to do the eigenvectors for I, so I can do them, but if you guys want to see that. Oh. Okay, then I'll skip on the I, but I guess if it was like going into complex, then yeah, you would probably have to do the I ones. Okay. For part C, we're just computing the eigenvectors, and then since we only have one eigenvalue then, for lambda equals 2, we take the matrix A minus lambda I, which is 2 in this case, so we subtract 2 from every thing in A entry, I guess. And we get -1, -1, 1, 1, -2, 0, 1, 1, -1. From this, we continue to row reduce echelon form to get the equations for the eigenvector. So we can take R2 plus R1, R3 plus R1, and this gives us -1, -1, 1, 0, -3, 1, 0, 0, 0. And once we have that, we can do a little bit more. So we can take multiply -1 to R1 and multiply -1/3 to R3, just to make it all row reduce, right? So 1, 1, -1, 0, 1, 1/3, 0, 0, 0. And we can take R1 minus R3. Oh, no, not R3, R2. And go 1, 0, -2/3, 0, 1, -1/3, 0, 0, 0. Since we know that A minus lambda I is equal to 0, this means that if we set let's say this is our eigenvector, equal to x, y, z, x is equal to 2/3 z, and y is equal to 1/3 z. And if we can set z to anything we want, so let z equal 2, 3, just to get rid of the fractions. And then from that we get x equal to 2 and y equal to 1. Therefore, our eigenvector for this question would be 2, 1, Okay, moving on to part D. So part D is asking us to use the eigenvectors of A to get the eigenvectors of T. This just means that we want to write the eigenvectors in terms of the alpha basis. So that would be alpha equals to 1x squared. We just want to write it in the polynomial form. So the eigenvectors of T would be then let me see, I wrote it down somewhere. 2 plus x plus 3x squared. And this is our only eigenvector. Moving on, I'll be doing question 4, and we'll go back to question 3 when the next person takes over. So question 4 asks us, suppose A is an n by n matrix, prove that lambda equals 0 is an eigenvalue of A if and only if A is not invertible. So for this solution, recall that an eigenvalue is defined such that there exists a vector v where AV is equal to lambda v. We also know that for lambda to be an eigenvalue, it has to fulfill A minus lambda I. Its determinant is equal to 0. So let's prove the forward. So lambda equals 0 implies A is not invertible. Directly. So if lambda equals 0, this means that lambda equals 0 fulfills A minus lambda i's determinant equal to 0, which means that A minus 0 times I is equal to 0, which means that A minus A, the determinant of A, is equal to 0. Since we know that the determinant of A is equal to 0, we now know that A is not invertible because by definition, an invertible matrix has a determinant not equal to 0. Okay, now we got to prove the backwards because it is an if and only if question, right? So A is not invertible. Implies that lambda equals 0 is an eigenvalue. Let me write that down, eigenvalue. So from this, since we know that A is not invertible, determinant of A is equal to 0. From that, we can add like a 0 vector to A in the determinant, and it won't affect the determinant at all because you're adding a 0 vector, right? So A minus 0I is equal to 0. This implies that determinant of A minus lambda I equals 0 when lambda equals 0. From here, we can see that lambda fulfills the condition to be an eigenvalue, to be an eigenvalue. Therefore, what is it? If A is not invertible, lambda equals 0 is an eigenvalue. And since we proved both ways, therefore lambda equals 0 is an eigenvalue if and only if A is not invertible. And that is the end of the question. Can we prove that this if and only if statement using equivalent statement? A is not invertible implies determinate. I'm not sure about that. I feel I've always learned the way that you have to prove both ways for an if and only if statement. So you have to prove forwards and backwards. I think doing it forwards and backwards for an if and only if statement will makes your proof more rigorous. So it won't be wrong for sure, but probably check with your TA or prof or something on proving it using equivalent statements for that. Well, in terms of errors in the proof, I'm not sure about that either. But usually when we're proving if and only if, you go one way and then the other way, even if you're using the same logic while going through it. It's best to start with the assumptions that you're supposed to have one way and then go the other way to make sure it works both ways. Otherwise, you're kind of like messing up what you start with and what you end with in your proof. Can we use the fact that determinant A is the product of all eigenvalues to show that if 0 is an eigenvalue, determinant of A equals 0? Yeah, probably. That does make more sense at all. I didn't think of that when I was doing the proof. I'd probably also go both ways to prove if and only if, just to be more rigorous on that. But it should be fine either way. But don't quote me on that. So, yeah. Can we use the fact that there will be a non-zero vector in the kernel for backwards, since it is invertible, so not injective? I think I kind of get what you mean, Kevin, but like you do need to like connect it back to like diagonalization and eigenvalues on that. So make sure you make a note of how the logic falls from that. Okay. That should be all the questions for this part. I'm just gonna move it on to the next person.
All right, let me share my screen. Hold on. Can I bring it here? Okay, so I'm gonna do something a bit different from what I did last time. I'm actually gonna go through it step by step, but I will
Next
okay
stop,
from time to time ask
Wasserheide.
questions.
Finish the airport. As a reminder, get on your Preston card.
Uh, Yeah, so sorry. Uh I will I will be asking questions as I go through with these proofs. So I would still encourage that you pay attention. Okay, so assume T is a diagonalizable linear map from V to V, right? Then show that V is the direct sum of the kernel of T with the image of T. Okay, so do you also remember uh, direct sums? Does anyone have like a definition for it or any characterization for it? Yeah, assume V is finite dimensional. Sorry. Dimensional vector space. Sorry about that. Well, leaving that out. W1 intersection W2 is equal to the trivial vector space if and for all V and V there exists W1 and W2. Yeah, so Daniil has it very close, and that was the characterization I was trying to prove on the te ter the term t the second term test review seminar. Um, so we need to show we need to show uh V is a subset of kernel T plus the image of T, right? So that's one. And the other way, so kernel T plus image of T is a subset of V is trivial because sums of subspaces are subspaces of V, right? So we have one subspace of V and another subspace of V, and you compute their sum, then that sum is also going to be a subspace of V. So we only have to show one and two, kernel T intersection with the image of T is just the trivial vector space, which is just the set with the zero vector. Okay, so we're already getting some ideas. So yeah, this is a good idea because if we're trying to prove certain elements, um or we're trying to prove like subset or set relations, then we need to show that given this set is in uh this set, let's say, so given a vector in V, you need to show that you can express it as the sum of a vector of a kernel T and a vector from the image of T. So those types of things, it helps a lot in linear algebra to have some sort of way to represent any vector uh, as like a linear combination uh, of like a finitely many vectors, right? So what John said here is because T is diagonalizable. This is the definition, I believe. Should have been the definition you were given about diagonalizability. There are also numerous ones, one about similarity of matrices, and maybe algebraic and geometric multiplicity of eigenvalues, but I assure you this is we'll just stick with with this characterization of it. So there exists a basis, let's call it I don't know, S. N of V, so that TVI is equal to don't really have a way of representing lambda. Just run with this. For each I in, let's just index it. 1, 2, 3, n. Yeah, I know. I don't have a better way. My latex thing doesn't work. I don't know why, but so yeah, there's a basis consisting of eigenvalues of t. Um, so sorry. Um, let's go through let's try to prove claim 1, right? So as always, you take an arbitrary vector in V, right, in the vector space. As now we have a basis of V, we can write it as a linear combination. So V is just uh 1, 1. Oh, wait, hold on. Let me this down. Where A1 to AN are in F. F is being the field of V, right? The field that V is defined on. Now, the question is, how do you write this as a sum of a vector in the kernel of T and a vector from the image of T? So it's a good idea to ask at this point, when is well, like what is there a way of like representing vectors um using vectors from this basis that we created? Is there a way to represent the vectors that are in the kernel of T, right? So if we think about it for a sec, I'm just gonna write something rough here, but let's say TV1 just equal to 0, right? We're not including this in our final proof. I'm gonna erase it out later, but let's just say this is hypothetically this is the case, right? Then because V1 is an eigenvalue that corresponds to just run with this one, right? So you get something like this. But V1 can't actually be a can't, sorry, V1 is non-zero, right? By definition of an eigenvector. So that would imply that lambda 1 must be equal to 0, right? Now, instead of so this is going to be the general idea of what we're going to do. We want to basically collect all the, or find a way to index uh, all the eigenvectors that correspond to the zero eigenvalue, okay? And those are going to be in our kernel T. And additionally, we will claim that that all the other eigenvectors that do not correspond to a zero eigenvalue are going to be in the image of T, okay? So that's going to be our strategy for this, proof claim 1. So let's define the set J in set of all elements in our indexing set I such that oh, lambda J 0. All right, then consider we're just gonna have to run with this. J in J, AJ, VJ plus J in I minus J. So what I mean by I minus J is all the vectors in I that are not in J, right? Or in other words, all it's a way of indexing all the eigenvectors that do not correspond to the zeroth eigenvalue if T has one. Now, I further claim that this will be a candidate in the kernel of T, right? And why is this the case? Well, consider you map this through T. Okay, so where do you think we can go from here? Does everyone have any ideas? We want to show that it's in the kernel of T, so we want to show that if we map this vector, it's a summation. Do you know what a summation is? Yeah. Basically, I'm just trying to tell you, add up all these terms that are indexed by J. So, but essentially it's just addition, right? We're just doing addition, considering elements. Okay, but what's the next step? Like, how do we get there though? Um that's a pretty large jump, right? So what is like, can you just tell me like one step that will help us like get us linearity? Yes. Linearity. So by linearity of T, because T is And now, as John said, we can apply, this is just lambda j, but because j is in j, right, this is just 0j, right? Oh, I don't know, let's just say by definition of j, and Bj is eigenvector. Okay. And then obviously this will just give us the zero vector. I can't really denote that, but uh 0 in, I don't know, we'll just with comma with brackets, additive identity of ESP. Okay. Now the slightly more interesting one is how would we, I guess, show that this is in the image of T? So by definition of image of T, we want to show that we can find a vector in V that maps to it, right? So let's actually um, so let's start from here. And this might not make complete sense as to what I'm doing, but hopefully you'll see what I'm trying to do. So uh, and then here we'll divide it out by lambda. Okay. Uh, So here we just multiply and divide it by lambda k, and that is equal to 1. But the more interesting thing is why we can do this, right? And that is because we're considering um, we've indexed all these elements so that the vectors, each of these eigenvectors are in I, but not in J. So if it's not in J, that means the eigenvectors that the eigenvalues that the eigenvectors correspond to are non-zero. So we can actually do this division. This division is well defined because of that. Um, so I'll just write that as a note here. This is well defined as lambda k non-zero by definition of, sorry, by by definition of J. I should, or we could say I minus J, but I think J is probably closer to what it is. And then now we just have to, you see how we can get to finding a vector in the domain that will map to this vector? Anyone? Can someone give me at least like one step? Okay. All right, you know what? Forget it. We'll just, where's that? Oh, sorry. Actually erased the wrong part. But yeah, so we want to, because VK is an eigenvector, uh, we can do this. So as and then finally, again, we just use linearity of t and uh, yeah, this entire thing is in so so we actually proved that this vector is contained in the image of t, right? So because of this, thus we have proven claim 1. Now we move on to claim 2. Right, and that was that when we intersect it with the image of t, when we intersect the kernel of t with the image of t, that's just the trivial vector space. So we can do it by just showing that this is a subset of the trivial vector space. Because the trivial vector space is a subset of like every vector space. It contains like the 0 vector of like any vector space. So let's start by saying let y be in the kernel T intersection image T. By definition of intersection, y is in the kernel T, and this is just, isn't this a property of direct sums? Which, this thing? The claim, are we talking about claim 2 specifically? Um, yes, but we don't know that it's a direct sum. That's what we're trying to show. And the way we are trying to show it is by using this characterization, right? So trying to show that first you can get something like v equals kernel t plus image of t, and then proving this, right? Yeah. Well, hopefully that clarifies things. Um, and this is equivalent to saying ty is equal to 0. And then, and y is in the image of t. So this is just equivalent to saying there exists an x in v so that tx is equal to y. All right, so it seems like things are a bit unclear at this point, right? Because it doesn't like there's it seems like if you just played around with it, um around with like y and x and with t, then you might get somewhere, but actually the whole point of this part is to actually use to draw in the extra context that we established in the beginning of this question, right? So things like there exists a basis of V, right? Oh, look, we have an X in V. So we can actually we have more context to draw in from, and that actually makes the problem easier to solve because we have more information to work with, which allows us to make make more progress in terms of coming to correct conclusions. So as X is in V, we write X is just this finite sum of this. Or I could just say something like I equals 1, and then our n. I don't know which one. I'll just run with this one, but bi times bi, where n, you can just say b1 to bn are all in F. Then, okay, so now that we've written X in terms of the sum, do you think we can, what's the next step do you think that we can conclude based on, and also using like this type of information? Because we will have to use it at some point. If we assume it in our hypothesis, then you do have to use it somewhere in your proof. Otherwise, you did the question wrong. So does anyone have any idea? Okay, well, hold on. Okay, so we did characterize this X, and we did say that this X in V, so that if we mapped it through T, it does equal to Y. So maybe we can we can characterize this Y in terms of this linear combination, right? Or something very similar to this linear combination of vectors, of eigenvectors. So we get V in here. And then again, linearity of T allows us to write it like this. And then you all know where it's going. This is just, VI is an eigenvector. So we can now like lambda I as VI is an eigenvector. And then yeah, we can use associativity just to rewrite this entire thing like this. Okay. Um, so now that we have a way to represent y, we also have to work with this information, right? And it tells us from our assumption that ty is equal to 0. So let's try this. Let's start with, this is a bit of an unconventional way of doing this, but let's just run with it anyways, right? So we have this uh, again, T is a linear map, so we can just rewrite this like so. EVI by linearity of t. And then, oh wait, actually, hold on, let's just. Then this is again eigenvector. I know this kind of gets repetitive throughout the proof once you've already figured it out. I is an eigenvector. And then finally, we could just, again, using associativity and a bit of algebra, we can just pack this in as b to the power of I times lambda I squared. So if we want to conclude that y is indeed the zero vector, right? We know that each of these VIs, since they're all eigenvectors, they cannot be zero. So that means we must somehow get all of this to be, we must get have b1 times lambda 1 equals to 0, and then the same for all I from 1 to 3 all the way up to n, right? So given that, how do you think we can get there now? Because we do have a convenient setup. We have a linear combination of basis vectors now representing the zero vector. So what do you think is the next step? Uh, well, the lambdas aren't necessarily non-zero. You are correct that the eigenvectors are non-zero by definition of eigenvectors. Um, but the lambdas may, some of the lambdas could be zero, they may not be zero, but we can't conclude that they are all, the lambdas themselves are non-zero. Okay, this is a basis vectors. What do you know about basis vectors? No, but we're done. We're past the step of separating it between the kernel and the image. The whole separation thing was just to prove that this, right? There's just like you have B, yes, linear independence. There we go. So as S is a basis, it is linearly independent. So we get this thing equal to 0 for all I and I. And then from here we can just conclude that either BI is equal BI. This would imply that BI times lambda I is equal to 0. Why? Well, you can use algebraic laws on vector spaces. So if you have this times this equals to 0, then either bi is 0 or lambda I squared is equal to 0. Lambda I squared is equal to 0 if and only if lambda I is equal to 0. So now we have bi, either bi is equal to 0 or lambda I is equal to 0, which is which concludes that bi times lambda I must equal 0. Again, for all I in I. And also don't forget your connectives. And yeah, so therefore, y is just equal to this 0, and then this is just equal to the 0 vector as 1. Okay, so that was the question. I was wondering if we should take a break now, or should we move on to the next one? What does everyone think? Oh, okay, yeah. So first, try to screenshot this. Um, I do wanna, I do apologize for being late when I sent out my answer sheet for the last term. So I'll definitely send it immediately once the once the seminar ends. What about the other inclusion? So for which direction? Because I mean, in either case, like the other, in either, if I do the other subset relation, right, to show this, to prove set equality, it's all just going to be trivial, right? Like you can do it like on your own in like 1 to 2 sentences. Like that's usually not like the part that's going to be worth much, if anything at all. I mean you could mention it like in a line or something. So let's say like something like uh, uh this, something like that. But like again, this is like very trivial. Like I'm not sure if how extensive your teacher wants you to be. Um, but I know that even if you do mention it, it's probably not going to be worth much anyways. So like, and I think most teachers would actually just give you full marks if you mentioned like everything else, right? Um, okay, so we have two people saying break. One person says move on. Break after which question? Okay, so we have three people saying break, four, four people saying break, and one person saying let's going. Okay, five people saying break. So yeah, just take a 10-minute break and we'll resume. Uh, yeah. Okay, we're just gonna so we're just gonna move on to the next question. And then after this, I'll just move it on to the next presenter, okay? Okay, so let me zoom in. Okay, so let V and W be vector spaces and let T be a linear map from V to W. Also, assume V is finite dimensional. Uh, let I be the identity map on W, and I want to show that if T is surjective, if and only if there exists a linear map S from W to V, such that the composition of TS is equal to I. Okay, so um, this is an if and only if proof, so we'll break this down into showing one direction and then the other. Let's just start with this direction. So assume um, assume there exists a linear map S from W to V so that TS is equal to I. All right, so let's show that T is surjective. So we'll do this through definition, right? So we take an arbitrary vector in the codomain of T, which is W, right? So let W and set W be arbitrary. Now, does anyone have any idea what vector I should pick? So I want to pick a vector V in V. That V satisfies something, right? Or V is equal to SW, yes. SW and right? And I think you can kind of guess where this is going. Um, and also this is which is in V because by definition of S, right? So let's just state that. And then TV is equal to TSW, the choice of their choice of V. Then by definition of composition, we can write it like this. And then by hypothesis, S satisfies TS is equal to I. And then by definition of the identity map, this is just W. Therefore, not S, sorry. T is surjective. Okay, so this one was pretty easy. This other direction, however, is going to be a bit more tricky. It's gonna okay, it's not really gonna be a bit more tricky, but I don't think so, but it will require a bit more work, right? Because you need to show that there exists a linear map S that satisfies this. So that actually, anytime you're asked to show that there exists something, a very common strategy is to actually like provide like just like give an example of it, right? And then show that it satisfies all the properties that you want it to, right? Ts equals I means that S is in the inverse of T. S is the inverse of T, right? Um, I mean, I I don't exactly think so. I don't know. I have to look at the definition of composition, but it might be worth exploring. Um, but let's save that for another time. So we are going to assume that T is surjective now, and now we want to show that S exists and S that can satisfy this. So, so by definition of T being surjective means that for any view W, there exists a V that depends on W such that that comes from the vector space V so that T V W is equal to W. Um, I don't know, maybe I can draw something here. Hopefully it won't be like, oh, well, okay, so I kind of want to, anytime you have like multiple linear maps mapping from like a bunch of different vector space or a bunch of different like sets, right? It's usually a good idea to like draw out some diagram of who's mapping to where, right? So let's get two rectangles, usually represented in circles, but doesn't matter. I'm just trying to convey something at the moment. So we'll just call this V and call this W, right? Pictures, again, picture is not a proof, but it can sometimes motivate details, and I think this is one of those times. So you have, oh, where's, oh, I can't even draw. This is, oh no, not half one mate. Believe we said T. Yeah, so T mapped it here. We want, what we want is uh to create an S so that um T comp the composition of TS is the identity map, right? So in other words, we want to take uh every input of like, so when T maps everything from V to W, right? We want to consider every output of W and define S by mapping it, let's give it, sorry, a different color. So we want to map this back to here. And this is how we want to, that's how we want to define S, right? Why? Because if T is mapping, if T maps something like this to, wait, wait, was it TS or? Wait. Oh, hold on. No, no, no. Sorry. I messed up the diagram. Um, sorry. This is kind of embarrassing, but no. This is how, sorry, we're trying to construct S, right? So first we would map S. Did I actually mess up the question? I'm very confused now. Oh, wait, okay. Okay, so I did mess up both, not just the direction, but like where we start from. So I believe this should be the correct way of doing it. So we have an S. We want to construct S mapping like this, right? So that since T is surjective, or actually we want, let's pick a different color, right? T will just map like this, right? So when you feed a vector from W into TS, it'll just map back here, right? So this is how you want to do it. Hopefully that illustrates it better. Um, let's try to move this down here. So let's define S by SW is equal to V of W for any W in W. This is a well-defined because T is surjective, right? Because we were just getting this from the fact that T is surjective. So first we claim that T is linear, right? And then we also have to claim that TS equals I, right? So let's start with this one. Oh, then this proves, and then like after we finish proving these two claims, then this proves this direction, the forward direction. So preamble says T is linear. Oh, sorry, S is linear. Sorry. Good catch. We're not satisfying, we're not trying to satisfy S is injective, though. I'm not really, the question didn't really ask. I'm not really sure why that's concerned, but okay, sorry. I think we're just kind of running low on time, so I just need to push things forward. Sorry. Um, so take any two vectors in the domain and any scalar that's defined on uh, and any scalar, right? And then as T is surjective, what? Okay. As T is surjective, there exists vectors Vx and Vw in V so that T Vx is equal to X and T Vy is equal to Y, right? So by definition of S maps X to V of X and S maps Y to V of Y. So then in order to prove S is linear, we will use the fact that T is linear, right? We can map the vector C times Vx Y is equal to this by Lin, and then this is just equal to, I don't know where to put it. This is just equal to C times X plus Y, right? We're just pulling these from here, okay? By definition, and now, since we have this mapping this vector by T through T, and we get this, then if we map this through S, we should get that this is just equal this, which, remember, again, using these by our definition of S, that's just C times S X plus S Y. So this proves linearity. All right, now again, this part should be much shorter. So we can just prove that this is equal to the identity map by saying let W be in W, then TS will be mapped through W is equal to T W composition of linear transformations. And then this is equal to T, or actually there is a step we've kind of skipped in this. So again, because W is in W, as T is surjective, there exists. Actually, we'll just call these V naught, right? Differentiated things a bit. V naught and V, so that TV naught is equal to W naught. This is just V naught by definition of S because of this, right? So I don't know, let's just give it star, right? Because star. And then finally, we again, just W naught by star again. And then finally, you could also add the last statement like this, by definition, I. And we have every vector in W. If you map in TS, you'll get this, always get the same output as mapping it through the identity map. So therefore, this proves our claim that TS is equal to I. Okay, I'll replace the ampersands because I mean ampersand does, I don't think an ampersand really means anything in math. I don't think there's any symbol, but yeah, I'm just trying to say and. Okay, so hold on. You guys quickly take screenshot. This is just work. You want to take a screenshot now about it before we move on. Also, you can prove a very similar statement where T is injective if and only if there exists a linear map S so that ST is equal to I. But we won't be covering that in this seminar. Okay, so has everyone gotten a screenshot? I because I'd like to move on with the other hosts so that they can present their questions. Are we good with everything? Um, okay. So I'm just gonna assume that everyone has already taken a screenshot. If not, then I'll just send it in. I'll just drop it in the AMACSS community Discord as soon as possible. Okay. So I'm gonna stop sharing my screen, and the next presenter can present.
Yeah, hello. Can you guys hear my voice?
Yep.
Yep, okay. Let's start then. Okay, so for the first question, we have a vector space V, which is a vector space of all real valued functions. And we let U equal to be a subset of V. So it is the set of all functions F such that there exists a B real numbers such that f of x is equal to 0 if x is outside of the interval. And our task is to prove that U is a subspace. So does anyone first have any ideas on what first steps we have to take? This f x equals 0 proof non-empty. Yeah, you got the right idea. So first, to prove that some set is a subspace, first we need to prove non-emptiness. Then we need to prove that the set is closed under scalar multiplication, and then close under vector addition. But I think fx equals 0 doesn't work here because, oh no, actually, no, yeah, fx equals 0 will work. Okay. So, with the first point, we'll let f to be a real value function such that f of x is equal to 0 for all real numbers x. Then the only thing that we need to do now for this point is to prove that f is a member of U. So to prove that f is a member of U, we need to find real numbers a and b that satisfy the set property space. So does anyone have any ideas on what we can pick for a and b? Yeah. So yeah, any choice of a and b will work here as long as a is less than or equal to b. So I'll just use easy numbers. I'll choose a equals 0 and b equals 1. And we let x to be a real number such that x is not in the interval a and b. So we get fx equals 0. And by definition of the set, f is an element of U. I'm so lost right now. Yeah, I guess like this definition could be a little bit confusing. But what it's basically saying is we are considering the set of all functions such that there's a closed interval where outside of this closed interval everything is mapped to 0. So since f here is just the constant function 0, we can pick any closed interval that then anything will work because everything is 0 anyways. Any questions? Any other questions? What about the function? Here's the function that we chose. Yeah. Okay. Right. So I'll just continue on to the second point, which is proving closure under scalar multiplication. You can do this in one step, but I prefer to do it separately. So we let f to be an element of U, C to be element of our field, which is in this case is real numbers. And we want to prove that CF is in U. So we let A and B to be real numbers that satisfy the property of U. So such that f of x is equal to 0 for all x not in the interval a comma b. Then we let x to be any real number that is not in the interval a comma b. And here, cf of x will be c times f of x, which is 0. And this is by our choice of a and b. Therefore, a and b satisfy the conditions of our set. And hence, CF is also in A. So we choose A equals minimum and B equals. So yeah, that's what we're going to do for the second one. Yeah, you've got the right idea there, Aman. So for the closure under factor addition, we first let two arbitrary functions, f and g, to the elements of U. We want to prove that f of g is still an element of U. So we let A1 and B1 such that f of x, I must the real numbers here, f of x is equal to 0 for all x not in the interval. And similarly for g, we let A2 and B2 to be the corresponding variables for g. And then, as Ahmad said in chat, we let A to be the minimum of A1 and A2, and B to be the maximum of B1 and B2. And we let x to be a real number outside of the interval a comma b. Here you can make a couple of different arguments to prove our point. But I'll divide by cases x less than a or x greater than. If x is less than a, that means x is less than a1 and x is less than a2. If this means that f of x, g of x, which is equals 0, and this is just the definition of f plus g. Otherwise, we have x is greater than b, which implies x is greater than b1 and b2. Therefore, f of x plus g of x is also equal to 0. And again, f plus g of x is equal to 0. Therefore, by definition of U, f plus g is in U. So, and since U is closed under addition and multiplication and non-empty, it has space. So why did you choose min? So we're choosing min for A and max for B because we want to we want the choice of our x that is outside of the interval to be both outside of the interval a1 comma b1 and a2 comma b2. So I'll illustrate an example of f and g. So let's say this is a1 and this is b1 and this is a2, this is b2. So f will be this red graph here, which is 0 outside of a1 b1. Then it will take on some values here, some maybe non-zero values. Same with G. So G will continue to 18. We want to pick the axis in these area here. So outside of those and intervals. And the one way to guarantee it is we choose the minimum of the lower bound A1 and B2 and the maximum of the upper bound B1 and B2. So that when we add the functions together, we will still get 0. Does it make sense? Yeah, okay, nice. Great. That's it for this question. And yeah, we can continue to the next. So next, the A, B, and n by n real matrix with eigenvalue lambda. And we suppose that A is invertible. And we want to show that 1 over lambda is an eigenvalue of the A inverse. So again, any ideas? Inverse algebra? What do you exactly mean by that? First, by the definition of eigenvalue, yeah, that certainly will help. So there's this. A non-zero vector V such that AV is lambda Q. And where do we continue from here on out? What do you exactly mean by A goes in the other side? If we multiply both by the inverse, we get this. Yeah, okay. I think most of you got an idea of it. The maybe not the best way to write it down. So I'll just go over it. So we let V to be an eigenvector with eigenvalue lambda, such that V is non-zero. Lambda like half like the actual. And then we consider A times 1 over lambda of V. And since the eigenspace of lambda is a subspace, I believe you've proven this in class. 1 over lambda V is still in the eigenspace. That means this is equal to lambda times 1 over lambda V. I should just read And then here we can multiply A inverse by in both sides. Then by associativity, you can group these two guys up. So we get 1 over lambda v is equal to A inverse of, since v is non-zero, we get a 1 over lambda is an eigenvalue. And we're done. Any questions? Doesn't A need to be linear? A is a matrix. So A will be a linear, it will represent a linear transformation because it is a matrix. Do we state that lambda is not zero? Oh yeah, that's a good point actually. Yeah, yeah. Um, where would I put it? Okay, we can put a justification here. Since A is invertible, lambda is not zero. Well, so 1 over lambda makes sense. Should we state that lambda is not zero? Yeah, I did already. Does a 1 over lambda v is, yeah, it is. If there are no more questions, I think we can continue. Yeah, this is a nice observation. Okay. The next, we have A is an n by n real matrix with eigenvalue 0, and B is just an arbitrary n by n matrix. The question is to prove that 0 is also an eigenvalue of AB and BA. And to prove or disprove that this is true for any eigenvalue lambda. We'll do the first point, and we'll do the easier case first. How does it? Are you talking about the previous question? Yeah, the previous question 0 is not an eigenvalue. Here it is. Okay, yeah. Great. So I'll do the easier part first. Want to prove that 0 is an eigenvalue of the A. And here we can let V to be in the eigenspace of 0, such that V is not 0. And here we get that BA of B equal to B K of B, which is equal to B of 0, B times 0, which is equal to 0, which is equal to 0 times 3. Since V is non-zero, we get that 0 is eigenvalue of BA. Determinants. Yeah, we can also use determinant multiplicity, but I'm not sure if you guys have covered that in this class. Have you? Because I'm pretty sure in A22 you discussed it in mathematics. Huh. Yeah, I wasn't sure if you guys are allowed to use that or not. But yeah, if you were, that is an easier way to do it. So easy solution. Yeah, so this is an easy solution. But anyways, as an exercise, let's assume that we cannot use that fact. So we want to prove that 0 is an eigenvalue of AB now. Does anyone have any ideas? I think we're kind of tight on time, so I'm just gonna go. So I will divide the cases. So suppose um, suppose that there exists a W in the eigenspace of 0 such that V is equal to W. Then oops, so this implies that AB or ABV is equal to AB of V, which is A of W, and this is 0 since W is in the eigenspace, which is equal to 0 times W. Therefore, in this case, 0 is an eigenvalue. And in the second case, otherwise, for all W in the eigenspace of 0, there are no such Or here we can think of A and B as linear transformations since they are one-to-one with matrices. So we can say that B is not surjective. And this means that it is also not injective. And there's a C, which is not a zero vector, such that E of B is equal to 0. Or A B is equal to A B of B. Which is equal to 0 times U. So in this case, we also get that 0 is an eigenvalue. Right. Yeah, so we have covered all cases and we're done. Any questions for this part? So for the second question, we'll just need to come up with one counterexample. I'll let A to be the identity matrix of Rn to Rn. And we let B to be the zero matrix. One is an eigenvalue of A, since A of V is equal to 1 times V for all V. But B times A is just the zero matrix again. And obviously, 1 is not an eigenvalue of V. Eigenvalue of B times A. And yeah, we've got the counterexample that we want. So I think that's it for this question. If there's no questions in the chat, yeah, I'll just move on to the next one. So next, let V be a vector space and let W be a proper subspace of V. Let T be a linear transformation from W to V, and we need to prove that T is not surjective. Any ideas? So here we will use the rank nullity theorem. So since T has domain of W, the rank nullity theorem says that the dimension of W is equal to the dimension of the kernel plus the dimension of the image. So of course, the dimension of the image is equal to the dimension of W minus the dimension of the kernel, which here is less than the dimension of V. It's important that this is a strict inequality because W is a proper subspace. And since the dimension is non-negative, this is less than the dimension of V. Yeah, you can also say that. Wait, I'm not sure if you're allowed to say that directly, but I don't know. It depends. It depends on the instructions, I guess. Yeah, yeah. Thomas does that? Oh, well, okay. This is a bad question then. This is too trivial. Well, anyways, you can also do it this way. Yeah, and that's it. Therefore, T is not subjective. And yeah, that's it for my section. And I'll let the next person take over. Thank you and good luck on your final exams.
Hello, can you hear me?
Yes, we can hear you.
Okay. So I'll take 2 questions, and that's the first one. I'll give you guys like 1 minute to think about it. Okay, so it's quite similar to the one Thomas gave you for the question 9. So the first thing we want to show is like the dimension of by n matrix is Mn. That's quite straightforward. And we want to show, or we want to prove if T is linearly independent or not. So let's just assume T is linearly independent, because that can give us an additional condition. And we know, like, if T is linearly independent and T is in M, so we must have T less than or equal to dimension of this one. And that is but according to the conditions, we know T equals n plus 1. And this is greater than Mn. So thereby we have a contradiction. So our assumption must be false. Then we have T is linearly dependent. Yeah, by dimension bound theorem. This one's pretty straightforward. And we'll move to the next one. It's a computation question. I'll give you like additional 2 minutes so that you can fully compute it. We can see if you get it correctly or not. So for the dimension bound theorem, it's just that like so dimension bound theorem. So if let V be finite dimensional, vector space. And let beta be a subset of V. So if beta is linearly independent, then we have beta less than or equal to dimension. Okay, so to determine if A is diagonalizable or not, we need to do 3 steps. So first step, we want to find the eigenvalues. And then we want to find the eigenspaces, or like eigenvectors. And the last one, we just want to determine if it's diagonalizable or not. So for the first step, to calculate the eigenvalues, we want to calculate the determinant of the A minus I, lambda I. So that's 0, 2 minus lambda, 1, 1, 1, and 3 minus lambda. So to calculate the determination of a 3 by 3 matrix, there's one thing we need to pay attention to. We will let this be, we will let the first element to be the positive, and then negative, positive, in this order. So to calculate this, we get like positive 2 minus lambda, and then we want to multiply the determinant of this form, this matrix. Yeah. And because this 0, so again, we don't need to do any calculations. And for the last one is minus 2. So we'll get that 2 minus lambda and multiple 2 minus lambda, 3 minus lambda, minus 1. And that's minus 2 minus lambda. And therefore we get it's 2 minus lambda, 2 minus lambda, 3 minus lambda, minus 2 minus lambda, and we want to get this out. We want to get 2 minus lambda out and factorize it to be 2 minus lambda, 3 minus lambda, minus 2. I'm sorry. And plus 4. And we'll further factorize it, and it's minus 1, minus 4. So we want to set this equation to be 0, and we'll get 3 solutions. That's our eigenvalues. Okay, so so far we can also get the algebraic multiplicity. So we have 1, 1, and we have 1, 2, and last we have 1, 4. This will help us to when determining if the matrix is diagonalizable or not. Okay, so then we want to calculate we want to get the eigenspace space. Let's calculate a minus 2i. And that's is pretty straightforward. So we can know like this is free. So for lambda 2 equals to 2, we have geometric multiplicity 1. And then for a minus I, we'll get there 1, 1, 0, 1, 0, 1, 1, and 0, 0, 0. And then we'll get 1, 0, 0, 0, 1. Oh, wait. I'm sorry. I apologize. That's the... Okay, so this one is the free one. And we can also know the geometric multiplicity for eigenvalue 1 is also 1. And then a minus 4i. Yeah. And then we'll do the calculation. So I'll get and okay, I'll show the whole questions later so you can screenshot it. Oh, okay. I'm sorry, I didn't know this, but yeah, you can do this. I just wanted to show you like how you can calculate this step by step. And then faster for but we can use this as an example to calculate the eigenspaces. So for eigenvalue 2, we want to get the vectors, and we know that there is only one free, so there's only one vectors in our spaces, and this vectors should have like the third to be 0, and we want the first and the second add to 0, so 1 is 1. And that's pretty easy, and we'll just do the similar thing to the other two eigenvalues. And for eigenvalue 1, we'll get one, 1, 2. Okay, and so because, as you said, like if all the the algebra multiplicities are all 1, you don't have to check geometric. And so to determine it, we know that dimension or 3 is algebra 1 plus 2 plus 4. You can screenshot it if you want. Okay, that's the end of our review seminar, I guess. Do you have any other questions? Okay, then good luck on your finals. Bye.